Hi everyone, my name is Benedict. I'm a PhD student at the Communications Engineering Lab at the Cultural Institute of Technology, and I'll present in this video a temporal Gaussian noise model for equalization-enhanced phase noise. We have already presented this work at the European Conference on Optical Communications, so ECOC, in Copenhagen in September 2025. And this work is a joint work with Fred Bukhali and Wahid Aref from Nokia and my supervisor Laurent Schmalen, also at the Communications Engineering Lab at Cultural Institute of Technology. So let's dive right in. So next generation coherent optical transmission systems need to increase the symbol rate per channel in order to simultaneously increase the throughput and decrease the cost per bit. However, when we transmit a symbol over the optical fiber, it broadens. And this accumulated dispersion, so the temporal broadening of the symbol also increases with the symbol rate. Therefore, we usually apply a digital chromatic dispersion compensating filter at the receiver, which squeezes this broadened symbol again together. However, here at the digital CD filter, we require a constant LO phase. However, like you can see here, the LO phase is not longer constant during this received broadened symbol. And so when we apply the CDC filter, the LO phase noise is squeezed together, and then the interaction between the CDC filter and the LO phase noise leads to a distortion, which we call equalization-enhanced phase noise, or short EEPN. So EEPN causes burst-like SNR degradation, like you can see here on the right hand side. However, the state-of-the-art models EEPN still as additive white Gaussian noise with time invariant distortion power. This model underestimates the impact of EEPN because such burst-like SNR degradation increase the risk of uncorrectable blocks after the forward error correction. Therefore, we need for fast and accurate system simulation or performance prediction a simple model which describes these SNR fluctuations. And this is what we will provide in this talk. So we propose to model all impairments, including EEPN, as additive white Gaussian noise with time-varying variance. And so this time-varying variance consists now of a time-invariant part, which accounts for amplified spontaneous emission, fiber nonlinearity, and transceiver impairments, and now the novel EEPN distortion power, which is time-varying and which we need to derive in the following. So actually I won't go through the full derivation, but just give the key ideas and results of the derivation in this presentation. So say in this presentation we consider a minimal system model, since all other impairments have a negligible interaction with EEPN, so we consider a minimal system model in which EEPN is the sole distortion. So we pass transmit symbols through a CD filter modeling a dispersive fiber. Then we add an arbitrary LO phase noise realization, so our model does not make any assumptions about the LO phase statistics. Then we apply a CDC filter, digital CDC filter, and finally we apply a fully data-aided carrier phase recovery, in particular an ideal data remodulation. So at OFC earlier this year, so in March 2025, we showed that equalization-enhanced phase noise is actually a time-varying frequency-dependent phase noise and can be modeled by a time-varying all-pass filter with a phase response phi EPN, and manifests as a time-varying frequency-dependent phase error after the carrier phase recovery. So a phase error which depends on the time or the symbol index L and the frequency. And so now one key result of this presentation or this paper is now that we can express this instantaneous EEPN distortion power as the mean squared frequency dependent phase error. And here we take the mean along the frequency axis. And the frequency dependent phase error itself is given by the difference of the frequency dependent phase noise and the carrier phase recovery estimate. And so this is already a very nice result. However, we can find also a second expression for this EEPN distortion power, or a more closed form expression of the EEPN distortion power, when we determine here this frequency dependent phase noise and this carrier phase recovery. And so now in the following we will see how those two terms actually look like, and then derive a second expression for the EEPN distortion power. So let's start with the frequency dependent phase noise. What you can see here is now an LO phase noise realization during the CD induced memory, so during the accumulated dispersion. And so if we now apply a CDC filter to this LO phase noise, this results in a frequency dependent delay. And this transforms here this LO phase walk off over time into a frequency dependent phase noise. So the phase response of our EEPN all-pass filter is determined by the LO phase walk off over time. So in particular here the phase response of our EEPN all-pass filter at time or symbol index L and frequency bin K is actually a delayed or advanced version of this LO phase walk off over time during the CD induced memory. So now the carrier phase recovery does not longer see does not longer estimate and compensate the instantaneous LO phase noise. Instead, it sees a frequency dependent phase noise. And so now the carrier phase recovery estimates and corrects the mean frequency dependent phase noise, which is equivalent to the sliding mean of the LO phase walk off over time with the CD induced memory as window length. So, and with these two insights, we can now derive here a second expression for the instantaneous EEPN distortion power. Namely, we can express it as the sliding variant of the LO phase noise with the CD induced memory as window length. So now to validate our model, we carried out simulations and experiments in which we measured the SNR and the LO phase noise realization. So we generated a 130 gigabaud signal, transmitted it over 1,900 kilometers using a circulating loop. And finally, we used a local oscillator with a line width of 210 kilohertz to coherently detect the signal. To measure the LO phase noise realization of the local oscillator, we mixed the LO with a low line with a reference laser and then used a second coherent receiver to measure it. To remove the time-varying frequency offset between the two lasers, we subtracted a fifth-order polynomial approximation from the measured phase and interpreted the residual as the phase error. In the simulation, we transmit now the same data and use the same parameters as in the experiment. And so in the simulation, we upsample, apply pulse shaping, SED filter before we add AWGN and LO phase noise. And now in our simulation, we apply this experimentally measured LO phase noise realization. In the simulation, we then apply static DSP, meaning CTC filter, matched filter, and ideal data remodulation. And in the experiment, we apply adaptive DSP, which additionally includes a frequency offset compensation, retiming, a CMA, and a post-equalizer. And finally, we calculate the SNR for blocks of 500 symbols. So here you can see now such an illustrative SNR sequence of our transmission experiment. And here we can clearly observe the burst-like degradation caused by EEPN. In our full system simulation, we applied the experimentally measured LO phase noise realization, and therefore we can observe now in the simulation the same burst-like SNR degradation like in the experiment. In contrast, the state-of-the-art, which models EEPN as additive white Gaussian noise with a time-invariant distortion power, here yields only or leads to a constant SNR penalty. So here the small fluctuations stem from the short averaging length when calculating the SNR. And now in contrast, our proposed temporal Gaussian noise model matches the observed burst-like SNR degradation caused by EEPN. And yeah, this already validates our model so that our temporal Gaussian noise model can reproduce this burst-like SNR degradation which we observe in the simulation and in the experiment. So to complement this illustrative example by a statistical analysis, you can see here now on the left hand side the distribution of the EEPN distortion power, and on the right hand side the correlation coefficient between the measured and the modeled EEPN distortion power. And so the first thing we can observe is that actually the burst-like EEPN distortions cause extended tails here in the distribution of the EEPN distortion power. So the state-of-the-art fails to reproduce those extended tails and shows almost no correlation with the experimentally measured EEPN distortion power. In contrast, our proposed temporal Gaussian noise model reproduces these extended tails and shows a very high correlation with the measured EEPN distortion power under static DSP. Interestingly, the correlation reduces for adaptive DSP. And therefore, we have to remember that we actually made two steps in the derivation of the EEPN distortion power. So first, we showed that the EEPN distortion power is the mean square, or is given by the mean squared frequency dependent phase error. And if we now calculate the correlation of this experimentally measured EEPN distortion power and the mean squared frequency, or experimentally measured frequency dependent phase error, we obtain still a very high correlation, which confirms this identity. And so then in the second step, we showed that the frequency dependent phase error is determined by the LO phase noise. And this is always true for a static DSP, which we assumed in the derivation, or in our derivation. And it is also almost in every instance, or this is almost the case in every instance, if we use adaptive DSP. However, when we have here a frequency dependent phase error, which has a linear slope, this frequency dependent phase error, or EEPN, manifests as a timing offset. And since the adaptive DSP includes a timing recovery, which can compensate timing offsets, this adaptive DSP can compensate EEPN sometimes partially. And so when adaptive DSP is used, this relationship between the frequency dependent phase error and the LO phase noise is sometimes, really at only a few instances broken, and this is what leads to this reduced correlation. So our temporal Gaussian noise model actually accurately predicts the burst-like nature of EEPN, so these as burst-like SNR degradation. However, a few of those bursts are compensated by the adaptive DSP. So let's conclude. EEPN causes burst-like SNR degradation. Therefore, we proposed a temporal Gaussian noise model. Here we derived the time-varying EEPN distortion power as the mean squared frequency dependent phase error, or as the sliding variance of the LO phase noise. Then we validated this model through simulations and experiments. So now the big question, what can our model be used for? So you can use it, for example, for accurate and low complexity performance prediction as a baseline for future EEPN mitigation algorithms. So to check how much EEPN do I have at a specific point in time, and how much does my compensation algorithm or mitigation algorithm improve the performance. And finally, in a generative manner, to model EEPN impaired links with only 3 lines of code. So our proposed temporal Gaussian noise model is much faster than this full system simulation, and it's also very, very simple to implement. And so if you are now interested in our model and want to play around with it, we uploaded a Jupyter notebook and a MATLAB live script to GitHub, so you can play around with our model and see how well it really matches the full system simulation, and also how fast it is. And then thank you for your attention, and if you have any questions, don't hesitate to send me email. Looking forward to your questions and your feedback. Thank you for watching.